Welcome to 8th in the series of lectures on simple machines. In this video we're going to focus on pulleys, but before that a quick recap of what we have looked into so far. We looked into classification of levers. We had class 1 lever, class 2 levers and class 3 levers, and for all these levers we found that your mechanical advantage is efficiency times velocity ratio, and in an ideal case that's equal to mechanical advantage equal to velocity ratio, and your velocity ratio is defined as your distance moved by effort arm divided by distance moved by load arm, and mechanical advantage is load by effort. So all the definitions and terminologies holds good for a pulley as well. So in pulley your load is given by this one, and the effort that you put in is given by the effort. So your effort is transmitted to the load using the tension of the rope. So these are the tension of the rope, and usually your tension of the rope is is in an ideal case all these are equal. Your tension and load and effort are all equal. So you don't need to represent T, but at least your load and effort needs to be represented. And let's say your load is let's say 50 kilogram force. In this case your effort as well would be 50 kilogram force. Your mechanical advantage is 1 here, because whatever load is there you have to put in your effort. So your mechanical advantage equal to load by effort, that's equal to, in this case, 50 by 50, and that's equal to 1. And your velocity ratio is given by the distance moved by your effort arm. So you move this rope, this hand, you move down by a distance of x. You know that this barrel is also going to move up by a distance of x. So usually your velocity ratio, which is given by the distance moved by effort arm by distance moved by the load arm, is also going to be 1. And this is in ideal case. This is in ideal case, right? Now in a non-ideal case, in a non-ideal scenario, your velocity ratio is going to remain same, because as long as your string is not stretching. So it's the distance moved by effort arm by load arm, which is equal to x by x, and that's equal to 1. And let's assume your pulley has an efficiency of 80%, so due to various reasons like friction and so on. So your mechanical advantage in this case is going to be efficiency times the velocity ratio, which is the same as levers, and here it's going to be 0.8 because that's equal to 80% into velocity ratio is 1, and so hence your mechanical advantage is given by your load by effort. That's equal to 0.8. So your effort would be a little more than your load, which is 50 by 0.8, and that's equal to about 62.5 kilogram force. So in a non-ideal case your effort would be a little more than 50 kilogram force. Now such a pulley is called a simple pulley, wherein you have only one pulley, and you are using a rope to pull something up. So if in case of a simple pulley your mechanical advantage is equal to 1, which means your load is equal to your effort, then why do you use a pulley? Why do you use a simple machine? The only reason why you use a simple machine is because a simple pulley helps in changing the direction of effort, right? Now you could have as well pulled this barrel up by standing by standing up somewhere, right? You could have pulled this up, but then that would be a lot more uncomfortable, because all your effort is going to be on your arms, wherein if you are able to lift something up through in such a scenario, right? A bucket of water from a well or something. So as you're pulling this rope, you are exerting force with your leg. So you're putting your leg also into work. So you're exerting a force downward, and also you're exerting a force with your hand. So both your hands and legs are working, and in this particular case, your legs are not working and your only hands are working. You use a simple pulley to reverse the direction of motion, so that it's much easier for you. But still, you don't get any significant mechanical advantage in this case.